go. You're on.
Alright, so this is our human error test part 1. We have a 2 kilohertz sine wave generated on our function generator hooked up to our oscilloscope, and here you can see on the tech scope it's 2 kilohertz, about 2 volts peak to peak, which is what we want in our test. And now we're going to capture from our Python interface. There's the signal that our scope is measuring. The PGA gain is all the way up, as this is a fairly small signal.
Capture that as the baseline, because we need a baseline capture.
Right. So we'll go ahead and pause this for a moment. Capture this. Put it on my flash drive, and we'll call this human error 1 baseline.csv. Okay. Good. So we have that. And now we're going to test with a couple of devices nearby. Actually, we've already got the lamp running. We've got a computer nearby on the left-hand side, which frankly isn't going to do a whole lot considering we've got a computer right next to it measuring anyhow. But the real test is going to be this blender over here, which blenders are notoriously electrically noisy. It is a solid 3 feet away by measurement with our yardstick.
So do you want me to turn on the blender and capture the CSV?
Alright, let's do it.
So we're going to turn on a blender, everyone, just for a second.
There you go. There are a couple little glitches that seem to happen. We'll go ahead and grab a waveform.
Did we already grab it?
Yep. Okay, and we'll call this human error
That'd be cool. Will it?
blender.csv.
Right.
There you have it. We'll be back in a few minutes here when we... Actually, no, we'll keep going.
Why not?
Sorry. Yeah, why not? We'll just plug right in and do it right now. Go over here, and we'll do our THD calculation, which Alex is very good at this point.
Woo! What are those called? The two that we have?
They were blender, human error tests.
Up at the top.
Baseline and blender.
Okay, so first we're going to just pull out the necessary data, which they're both on channel 1. So we will we'll call the first one data. Haven't used that before. Whoa. Jeez, Cobby, could you name it anything longer?
Sorry, I wanted to be specific. A little more specific than data.
Actually, it's already imported as data. No, I haven't even imported it yet. Okay, that's what the problem was. I'm an idiot. It's not your fault. This is going on YouTube. Is that okay? Alright, sorry. Now we are importing the data.
Tends to be a prerequisite for...
Yeah, for doing calculations with the data. They are data 1 and data 2. And so now we're going to say, or data 0. Anyways, now we're going to say data 1 is equal to data. We want all the samples in the first channel. Data 2 equals data. All the samples in the first channel again. Now we'll take a nice little THD calculation of the first sample, the baseline sample. And, oops, I have to define how many harmonics we want to calculate it for. We'll do 20 harmonics. That should be sufficient. And it gives us a nice fundamental frequency, which is 2 kilohertz, like we would have expected, and we have 1.9% total harmonic distortion, still well below our 5 value that we are always shooting for. Now let's calculate it for our second signal with also 20 harmonics, a little higher as you would expect with a blender on nearby, about 2% total harmonic distortion, still well below 5. The last thing that we need to check is that the peak-to-peak values are not more than 5% different. So I have a nice little peak-to-peak script that I'm going to run here on the first data set. And Our peak-to-peak value is 2 volts. Is that what it's supposed to be? Mm-hmm. Okay, 2 volts. Shows you what I know. And the peak-to-peak value of our second, wow, they're exactly the same. So we measured the exact same peak-to-peak value on both data sets. So the peak-to-peak values are obviously within 5% of each other. That should fulfill all the requirements for this test. So I will post both of those scripts on the website as proof, along with the CSVs that we captured.